Greetings, fellow South African learners. My name is Enhlanzeni, who is lecturing in Enhlanzeni TVET College under the Engineering Department at Nelspruit campus, Electrical Infrastructure and Construction. The subject that we'll be looking at today is Electronic Control in Digital Electronics, NQF Level 4. Our topic is based on what we call fundamentals of electronics. So, our module today is based on what we call basics of oscillators. Basics of oscillators. Well, you might be asking yourself, what is oscillation? Why do we need oscillation? So, if you were to think, you go way back, there was an object called a pendulum. Oscillation can be basically defined as a movement of an object back and forth at a given speed. So, what is an oscillator, or what are oscillators in electronic or in electrical world? An oscillator in an electronic world, we say it's an electronic circuit that can produce periodic oscillations of electronic signals. They are often in form of a sine wave, square wave, rectangular. You may have other forms of waves. So it is also capable of converting a DC power into an alternating current power. So, what does that mean? In a block diagram, an oscillator can simply be described in a fashion like this, where we say we might have a DC and the output being an AC. So here I will simply write os. So each time I write OSC, you know that it represents oscillators. So, where are the oscillators being used? Where we say applications. First of all, telecommunications. You guys who are interested in telecommunication studies, you should be very close to oscillators. They are the backbone of what we call telecommunications. Why telecommunications? Think of a voice. A voice is some kind of energy. It loses power as it moves distances. So it will be needed to be traveled over long distances. So for that to happen, transmitters in telecommunications need to ferry this voice over long distances. So for that to happen, transmitters must have what we call oscillator circuits, which will generate high frequency signals which are capable of moving those signals over long distances. Number two, optical communication. Nowadays we are talking of fiber optics. Fiber optics for everything, fast, quick and everything. So what does an oscillator do in fiber optics? It generates a periodic pulse of the light so that the communication can run smoothly. Watches and counters, your watch has oscillators. Calculators have oscillators. They generate counters and they keep the track of time. Nowadays, computers that we are using, they have what we call microprocessors. Microprocessors, they determine the speed of operation of your computer. So they need what they call a clock. A clock can be provided by oscillators. So that is where oscillators are being used. Now you can understand what an oscillator is and where are they used. You should be able by now to explain what an oscillator is and where oscillators are being used in our electronic world. Well, for oscillation to occur, we need to have some kind of circuits that can generate oscillations. We call those kind of circuits tank circuits. It's a simple connection of an inductor or a capacitor and an inductor. I will simply use the circuit symbols. By now we all know that in engineering we are using symbols. We just talk by diagrams. Okay, so this will be our capacitor and this will be our inductor. That will be our supply voltage, this will be our switch. So this is simply called a tank circuit. What do we call this? A tank circuit. This circuit is capable of producing what we call oscillation. How does that happen? Let's look at it in a nutshell. If we can say we apply a certain voltage over this circuit, we close switch 1. The capacitor will tend to charge to its maximum voltage, which is equal to Vs. Okay, so if we were to remove the switch, or if we remove the source after that, it simply means that our capacitor will still have this charge. That's the main function of a capacitor, storing charge. It can store this charge indefinitely, we say in electronics. We don't know how long it will keep this charge, but we know for a fact that for the capacitor to discharge, it needs to see some kind of resistance, some kind of a load across its two terminals. Okay, now, assuming that the capacitor is fully charged, and now we close this circuit like that, the capacitor will tend to discharge because now it sees a load. Remember, there is inductance and resistance in a coil. So it will see some kind of a load and will start to discharge its current to the inductor L1. So now, according to the laws of Lenz, if current flows through an inductor, some kind of a magnetic field is being created. So an inductor can store energy by some kind of a magnetic field. So once it has that, the capacitor will discharge completely into the inductor, and the inductor will now have maximum energy across itself. The laws of Newton says that energy has got the tendency of moving from a higher potential to a lower potential. By then, the capacitor is at a lower potential. So what does that mean? The magnetic field again will fall back into the inductor. Once it falls back into the coil, current will take the opposite direction, back to the capacitor. So when the capacitor is being charged, it will charge again by the falling field over the inductor. So now the inductor will discharge completely, leaving no magnetic field. The capacitor will be at its maximum charge. Again, energy is at a higher potential, lower. What will happen? The capacitor again will discharge back into the inductor. When it does that, the inductor again creates a magnetic field as it has done before. So you can see that these two components, our inductor and our capacitor, will keep on exchanging this energy in between them. So that is what we call oscillating, because they keep on changing the energy in between themselves. This can happen if we were to ignore any losses and any other kind of losses due to heat. We will say this process will continue for an indefinite time, which we don't know. So, but due to losses, it will tend to decay, or what we call to dampen with time. So that is how oscillation is being achieved. So we can prove the speed or the frequency of oscillation by some kind of a formula, where we say we know that for oscillation to happen, some kind of resonance must be achieved. Resonance from level 3, we know that XL must be equal to XC. That is our inductive reactance, and this is our capacitive reactance. The reactance that will be offered by the capacitor and the reactance that will be offered by the inductance. Mathematically, it is known that XL is given by this formula, which is 2 pi FL. and xc is given by this formula, which is 2 pi fc raised to the minus 1, or 1 over 2 pi fc. So we can now determine how much time will it take for this to alternate or to do the oscillation. So for us, we can simply say, if we want to know the frequency of oscillation, the speed at which these two will keep on exchanging the energy, we can now manipulate the formula and say 2 pi f squared LC is equals to 1, if I were to say. So then, from there, we will not go deeper into the mathematics of it, but it will simply tell us that 2 pi f squared is equals to 1 over LC. Therefore, 2 pi f shall be equals to the square root of LC. Then, making f the subject of the formula, which will give us our frequency of oscillation, it shall be equals to 1 over 2 pi the square root of LC. So, for us to know how frequent this will happen, we need to understand that frequency of resonance is equals to 1 over 2 pi square root of LC. That is to mean that if you were to know the value of your capacitor in farads and your value of your inductor in henries, you will determine the frequency of oscillation. Let me put one example so that we have this and understand. If I were to say in an exam, determine the frequency of oscillation for an LC tank with values L equals to, let's say, 100 millihenry, where C is equal to 50 microfarads. So this is one typical exam question which can be posed. For you, you now know that the frequency of oscillation, our solution, you now know that the frequency of oscillation FR is equals to 1 over 2 pi square root of LC. Let's substitute 1 over 2 pi, which is a constant, the square root. What's the value of L? The value of L is 100 millihenries. So it's 100, remember, it's milli minus 3, multiplied by 50, which is our C, which is 50 microfarads. 50 times 10 minus 6, it's in microfarad state. So you would, if you were to punch your calculator, you will find that your frequency of oscillation is equal to 71.76 hertz. It's measured in hertz, which is our unit of standard. So, that being said, now you can tackle how you achieve oscillation, how do you calculate the frequency of oscillation of a certain tank circuit, and you can also find that frequency of oscillation. Well, and good. How does an oscillator work? How does an oscillator work? Now, let's look at how an oscillator works. How does an oscillator work? I will use a simple block diagram to explain how an oscillator works. In an oscillator, we have, let's say, initially we have our input signal, we have an amplifier, and then we have a feedback path. So, now, we are talking of this as a block diagram of an oscillator. Simple, we know by now that for us to find V out, it shall be equal to the gain times V in, the gain of the amplifier times V in. So it gives us V out. So a certain fraction of V out is taken back into the input through what we call the feedback circuit. So feedback simply means taking our output back into the input. So now, if we look into that, we have our signal here, which is being taken from the output back into the input. So how does the oscillation occur? So that is our V out. Here we have our V feedback, which is now given back by our feedback circuit. It can also be mathematically expressed by some kind of AVB V in, beta V in. This simply tells us this is the loop gain. Loop gain. It simply tells us how much signal are we going to lose or gain during the feedback position. So now that you are aware of this too, then let's look at what happens. Let's say our loop gain becomes less than 1. Let's say AVB is less than 1. It means our signal will start at a very high voltage and then it will tend to dampen. We call it a damping signal. So you see our oscillations are decaying as time goes on. That's one condition. What will happen if our loop gain is greater than 1? It simply tells us that our signal will start at a very low and now tend to increase. So it is losing its oscillation as it continues to increase. So we need a feedback circuit which will give us a gain A, V, B, which is greater or equal to, say, equal to 1, slightly greater than 1 in practice. Okay, what does this mean? It means that our oscillation will be constant throughout. There will be no signal that is being lost. So that is a condition for oscillation. You will note that for a circuit to oscillate, we need certain conditions. This condition is a must in oscillation. It is sometimes called what we call the Barkhausen criteria. It is covered that if our loop gain is less than 1, our oscillation will decay. If loop gain is greater than 1, our oscillation will tend to increase. So it doesn't suit the value of oscillation. So condition number 1 for oscillation, the loop gain must be equal to unity, or what we say 1. Well, that's condition number 1. Condition number 2, oscillation must have what we call positive feedback. Well enough, we have a feedback, but the feedback must be in some kind of a positive format. What do we mean by positive format? A positive feedback has got what we call a 0 degrees phase shift, or what we call a 360 degrees phase shift. So somehow it must be achieved. If our amplifier is capable of giving us a no phase shift, it will be suitable for us to say that. But if our amplifier is giving us an inverted output, then we need to have some kind of circuits which will provide us with what we call a positive feedback. Okay, that's condition number 2. So if I were to write down these conditions, I would say the conditions of oscillation. Conditions of oscillation. 1, loop gain must be equal to unity. unity, or sometimes they'll say a gain of 1. 2, we need a circuit that will provide us with what we call positive feedback. Positive feedback. That is to say, our signal of the output and the input shall have a 0 degrees, or what we call a 360 degrees of what we call phase shift. That's positive feedback. And thirdly, obviously, we need a constant power supply. We need a constant power supply. So, those are the key conditions for oscillation. 1, it must have a loop gain of unity, positive feedback, which practices a 0 degrees or stroke 360 degrees phase shift. We shall also have what we call a constant power supply. So, now in your examination, they will ask the conditions of oscillation and ask you to describe them. By now you should understand what we mean by a loop gain, a positive feedback, and a constant power supply. So those are the conditions that you need to look into when you are dealing with oscillations. Now, let's look into what we call the types of oscillators we have. We are going into the types of oscillators that we have. The types of oscillators that we have. Types of oscillators. Types of oscillators. They are categorically distinguished into 2, mainly into 2. 1, we have what we call sinusoidal oscillators. 2, we have what we call non-sinusoidal oscillators. They are sometimes called relaxation oscillators. So, in our topic, or our next topic, we shall be looking into what we call sinusoidal oscillators. These are oscillators which shall provide us with what we call sine wave. Sinusoidal, they provide us with a sine wave. Non-sinusoidal oscillators, 2, non-sinusoidal oscillators shall provide us with any waveform. In most cases, it's a square or what we call triangular waveform. So, all those oscillators which cannot provide us with a sine, we call them relaxation oscillators. All those which provide us with a sine wave, they are called sinusoidal oscillators. Under sinusoidal oscillators, where we shall start on our next topic, but we need to know them now. Sinusoidal oscillators, they are sinusoidal oscillators. We have 1, what we call an RC phase shift oscillator. 2, we have LC oscillators. Oscillators which can be categorized as A Colpitts, B, a Hartley. Those are our LC oscillators. 3, we also have what we call a crystal controlled oscillators. 4, there's a Wien bridge oscillators. So these are the types of oscillators we shall be looking at. Under the sine wave, sinusoidal, we have an RC phase shift, we have an LC oscillator, which comprises of a Colpitts and a Hartley oscillator. These are the guys who discovered the behavior of these oscillators. We have a crystal controlled oscillator, and we have a Wayne Bridge oscillator. That is the end of our lesson 1 for now. Any further questions will be answered on our website, which is enhlanzenicollege.co.za, and we also have our media platforms, our Twitter page and our Facebook page. You can also go there for further clarification and answers. I thank you.